students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we will be doing this chapter called as EMI. Let's see another concept today. We'll see what are eddy currents. Now, we know that metals are made up of large number of free electrons and that's the reason why they are good conductors of heat and electricity. Metals have large number of free electrons, hence are good conductors of heat and electricity. Okay. Now when a metal is moved or when a metallic block is moved in a magnetic field or is subjected to a rapidly changing magnetic field, the free electrons which are present in the metal are acted upon by the forces of the magnetic field and they start circulating inside the metal block. Obviously, when you have magnetic field applied to a charged particle, it will result in a torque. So that's exactly what is happening. Electrons are charged particles. When they are acted upon by a magnetic field, when a charged particle is acted upon by a magnetic field, it results in a torque. So that is exactly what happens here, right? So I can say when metallic blocks are moved in magnetic field, the free electrons in the metal are acted upon by forces, whereby they circulate inside the metal block, right? This circular current which is set up inside the metal block is very similar to a whirlpool or an eddy and hence this is called as an eddy current, right? This circular current which is set up in the metal block is similar to eddies or whirlpool in liquids, hence they are called as eddy current. Hence they are called eddy current, right? So do we understand what are eddy currents? These currents were first detected by a scientist called as Foucault and hence some authors even refer to them as Foucault current, right? They were detected by hence also called Foucault current, right? Now let's apply Lenz's law to eddy current. Now what does Lenz's law state? The currents that are produced due to the change in the magnetic flux and hence according to Lenz's law, eddy currents should oppose the cause of their production. Lenz's law states that the induced EMF or the induced current opposes the very source that produces that current. So if I apply Lenz's law to this, I can say that eddy currents are produced due to the change in magnetic fields right, and according to Lenz's law, eddy currents thus should oppose the cause of their production, That means, that is, they will oppose the change in magnetic flux. That is, they oppose the change in magnetic flux. Fine, do we get this in here? Thus, circulating currents induced in a metal block, when it is moving in a magnetic field, are called eddy currents. Right? So do you understand what are eddy currents? Now eddy currents can be useful as well as harmful. Eddy currents can be useful and harmful. For example, in the case of transformers, right? You have large amount of eddy currents produced in the core of the transformer that causes large amount of heat loss in the core of the transformer. That is the reason why the core of the transformer is made up of multiple metallic strips, which is then coated by insulating material, right? So as to avoid the loss of energy, excessive energy, right? That's the reason why you have those laminated sheets, the multiple laminated sheets joined together to form the core of the transformer. Similarly, if I were to consider a dead beat galvanometer. Now in the case of a moving coil galvanometer, the coil gets deflected when current is passed through it, but as soon as the current stops, the coil tends to oscillate. It will not directly come back to zero. There will be some electric field, there will be still some magnetic field that will cause the pointer to oscillate, right? Now because of eddy current, these oscillations are damped and the pointer comes back to zero immediately, right? And that is called as your dead beat galvanometer, right? Do we understand eddy currents? Next, let's move on to the next topic. Let's prove Lenz's law. Prove that EMF is negative d phi by dt. Let's assume that you have a magnetic field. This is your magnetic field. Right? Now let's assume that I have a metal block that is going to move in this magnetic field. Let's consider a metal block that is going to move in this magnetic field. right? Let's say that this is P, Q, R, S, right? Let's assume that I move the metal block by a small distance dx. Let's assume that I move the metal block by a small distance dx. I move it till here, right? I move the metal block through a small distance dx, so this becomes my q bar, new value of q and new position of r. This distance is dx, right? Hence the metal block is going to move outwards by that same distance. This is going to be p bar and this is going to be s bar, right? Now let's try to understand the forces that are going to act on this. So first of all, I'll say consider a rectangular metal frame of conducting wire placed in a uniform magnetic field of induction B. Right? So you have magnetic induction B. Now, let's assume that the magnetic field is applied perpendicular to the plane of the figure. The magnetic field is applied perpendicular to the plane of the figure. Fine, do we get this thing here? Perpendicular to the plane of the figure. Now, let's see this. Let's assume that the plane is, if the frame is pulled towards the left, this is that movement of the frame towards the left, right? If the frame is pulled towards the left with a constant velocity of v, if the frame is pulled towards left with a constant velocity v, right? In that case, the free electrons in the wire will be acted upon by a force. The free electrons in the wire are acted upon by a force right? Now let's try to find out what is the force that will be produced there. Now, why they acted upon by a force? Because the electrons are charged particle, and any charged particle moving with a velocity in a magnetic field is going to be acted upon by force, right? Why? Because electrons are charged particles which are moving with a velocity of v in magnetic field B. Therefore, I can say that the force will be nothing but QV cross B. That is going to be the force that will be acting on the electrons, right? As the electrons are negatively charged particles, they will travel in anti-clockwise direction, causing a conventional current to flow in clockwise direction. Now let us assume that L is the length of the part QR. Let L be length of QR, part of the wire. Now as current flows through it, the force of magnitude, as current flows through the wire, as current flows through the wire, a force of magnitude BIL acts on the wire, acts towards right, and according to Fleming, acts towards the right according to Fleming's left hand rule. According to Fleming's left hand rule, if current flows through the wire, then the force is going to be in outward direction. So if current is flowing through the wire, the force will be in outward direction. That means the force will be towards the right. This force is in a direction which is opposite to that of the applied force. When I was pulling the metal frame, I was pulling the metal frame towards the left with a velocity of v, and the force that is produced is going to pull the metal frame inside. The two forces are in opposite direction. I can say thus, this force is opposite. This force is in a direction opposite. Is in a direction opposite to that of the applied force. Right? And opposes the motion of the frame towards the left, and opposes the motion of the frame towards left. Fine. So thus now we know that you have a force that is going to oppose this. Now the force also acts along PQ and SR. Force also acts along PQ and SR, but they are equal in magnitude and opposite in direction, and by Fleming's left hand rule they cancel each other. But the forces are equal in magnitude and opposite in direction, and hence by Fleming's left hand rule cancel each other. Right? Now, that means now the only forces are in QR and PS. Right? Now, in order to keep the frame moving towards left with the same velocity, it is necessary to exert a mechanical force which is going to be opposite to the force that is being produced due to current. In order to keep the frame, moving towards left with the same velocity, it is necessary to provide an external mechanical force. It is necessary to provide external mechanical force F, which is equal and opposite to the force, which is equal and opposite to the force F, which was BIL. Only then the metal frame will keep moving towards the left. Therefore, I can say that the mechanical force will be nothing but minus of F, that will be minus BIL. That is the mechanical force that has to be applied onto the metal frame. Now, if the frame is going to move it is going to move through some distance. There's some force, there's some distance. That means some work is going to be done, right? Let us assume that the frame moves through a distance dx in time dt. Therefore, work done dw. Work we know is nothing but force into displacement. In this case, work is done in the direction opposite to the applied force. Therefore, this is going to be negative F. This force is your mechanical force into displacement, which is nothing but minus BIL into dx, right? But I can say that dA is nothing but area of Q bar R bar R. Let's assume that dA is the area of Q bar R bar and R, right? In that case, I can say that L into dx will be nothing but dA, length into dx, length into breadth will be nothing but area. Therefore, I can say that the work done is minus BI dA, because L into dx is nothing but area. But by definition, what is B? B is nothing but the number of lines of force passing through unit area. But by definition, magnetic induction is nothing. Magnetic induction represents number of lines of force. Number of lines of force passing through unit area. That is my value of B. In that case, therefore, I can say that magnetic induction into area is going to be nothing but the change in magnetic flux in time dt. Magnetic induction into area by definition is nothing but the change in flux, when I can say d phi is the change in flux, number of lines of force in time dt. Right? So if I substitute this here, I'll get therefore dw is nothing but B into dA can be written as d phi into I with a minus sign. So this is, therefore I can say that dw is work done is minus I d phi. That is the work done in moving the metallic frame. Now this work is done by external force supplies certain amount of energy which is required to maintain the current, right? This work done by external force supplies some energy required to maintain current I. If there is work done in time will give rise to energy. That means therefore I can say work is nothing but EI dt. dw can be written as EI dt. Right? In that case, I can therefore say that EI dt is negative I d phi. Right? In which case you will get, therefore I and I gets cancelled. E is equal to negative d phi by dt. Thus EMF is nothing but change in flux upon time. Fine? Do we understand this? How do you prove this law? Right? Right. We'll stop this here for the day. Thank you very much.